Okay, in today's lesson we're going to look at different applications of the law of sines and law of cosines. The difficult part here is going to be coming up with a picture of the situation. Once you have your triangle set, it's pretty easy to figure out, using law of sines or law of cosines, the answers to the questions. First question, we have a forest ranger who is at ranger station A. He looks off in a certain direction and sees a fire. There's another ranger station 10 miles to the east, and he's looking at the same fire. They give you another direction there. So I've already drawn my initial picture here, so I just want to explain my reasoning a little bit. I start out, here's ranger station A, and 10 miles to the east is ranger station B. I thought that was the easiest thing to draw first. From there, I'm going to start with the directions. So from ranger station A, they say that it's 32 degrees east of north. In that direction we see the fire. Now I know this is going to sound confusing at first, but basically just do what it says. It says go 32 degrees east of north. So if we were to start by facing straight north, go 32 degrees to the east. That's what I've marked right here. And so you kind of get the general direction that you're going out. And then this total angle right here has to be 90 degrees. 90 minus 32 gets me 58 degrees. At ranger station B, again we start thinking straight to the north, but now 48 degrees west of north. So if I was going straight north, I have to go 48 degrees to the west, right there. That means there are 42 degrees left over, and all of a sudden I have a side angle side situation, and this is telling me that initially that I would use probably law of cosines, but if I think through what I'm trying to find, in the end here I'm going to try to use law of sines. It's going to be a little bit easier. So if I know two of the angles, very easy to find the third angle. Up on top there, 80 degrees, so 180 minus 58 minus 42 gets me 80 degrees. And I'm trying to figure out the distance from Ranger Johnson to the fire. Ranger Johnson is at station A, so I'm trying to find this right there. So based on the info that I have here, the easiest thing to solve here is going to be using law of sines. I know one length of the triangle, that's 10, so I need to set up its angle, sine of 80 over 10, and that's going to equal the angle opposite x, so sine of 42 over side x. Cross multiply and divide, and I get 6.79. It's an application question, so I want to label it. It's going to be in miles. Bada bing, bada boom, done. For second question, I should note here, I should have told you this at the beginning of the example, we're going to work our way from the bottom up, because the third question is the easiest, the second question is the middle, and the first question, for some reason I put that on top, is the most difficult. So in example 2, we're going to look at a baseball diamond. The bases are 90 feet apart, and we're going to look at the front edge of the pitcher's rubber. That's where the pitcher stands when he is throwing to home plate. And they tell you that that distance is 60.5 feet from the front edge of the pitcher's rubber to the back corner of home plate. And so one thing to note in my picture, I tried to exaggerate this a little bit, but the pitcher's rubber is not right in the middle of the baseball diamond. It's actually sitting back a ways. So 60.5 is not right in the middle. It's going to be back here more. And so that means that we can't just set up an easier type of equation, maybe dealing with Pythagorean theorem, because we won't have a right triangle here. But here's what we know so far. We know that the distance from the front center to the back of home plate, we know that distance is 60.5. Because this is splitting because this red line here is splitting the baseball diamond in half. I also know that the angle right here is 45 degrees. I know that all the base paths are 90 feet. And if I think about what they're asking me to find the distance from the center of the front edge of the pitcher's rubber, so right where this red line is coming off of the pitcher's rubber, and find that distance to first base, to the far corner of first base. So I'm trying to find X. And I know that this is 90 right there. And if I look at this, I have a side angle side situation. I'm trying to find that third side, and this would be a situation where I want to use law of cosines. So that law says figure out what angle you're dealing with, and the side opposite it is what you start out using first. So we're going to have an x squared equals, and we'll start out with 90 squared plus 60.5 squared minus 2 times 90 times 60.5. Oh boy, I'm going to run out of room here. Cosine of 45 degrees. Let's put that right down there. Okay, should all be one line. And I am fairly confident, after practicing this for a day yesterday, that you guys know how to solve for x now. So you go through all that algebra work, and when you are done, you would get x equals 63.72 feet. And if the pitcher's rubber was right in the middle of the baseball diamond, we should get 60.5 for that. So we're just a little bit off there. Moving on to example. Going back to this slide here for a second, one thing I just noted is that because of our measurements here, the pitcher's rubber is actually closer in, but it's still not in the middle, just closer in. Just happened to notice that when I was Okay, example 1. I did say this was the toughest of the three. And so we have a road that slopes 15 degrees above the horizontal. There's a vertical telephone pole that's standing beside the road. So what I'm trying to show you here is, here's the road, 15-degree angle. Here's our blue telephone pole, vertical. And we know the angle of elevation for the sun is 65 degrees. We're going to say that the pole casts a 20-foot shadow instead of 15, otherwise we got too many 15s in the question. So right here is 20 feet for our shadow. We want to find the overall height of the pole, so I've labeled that as h. Again, the biggest thing is going to be coming up with a picture of the situation. And so I've got a good start here, but all I have is one side of the triangle. You can kind of see a triangle formed right through here. And so we need to add some things to that. Several ways to do that. I want to talk a little bit about that 15 degrees above the horizontal. That means that wherever I were to draw a horizontal line with the road, I'm going to be able to put 15 degrees in there. So there's 15 degrees. Right here would be 15 degrees. Okay, that can kind of help me come up with some other numbers. For example, the angle that is formed from the telephone pole to here has to be 90 degrees. So 90 minus 15 gets me 75 degrees. And I also know that these two angles would have to add up to 180. And so putting those together, I know that this inside angle is 105 degrees. So now I have an additional part of the inside of the triangle that's going to help. Let's talk about the sun for a second. I know that if the sun is somewhere way up here and it's casting its rays down to the ground, the angle that it would form with a horizontal ground is 65 degrees. So if this whole angle right here has to be 65, I've already taken up 15 of them right there. That means the angle left over right inside is going to be 50 degrees. So that is the angle right in here. And now I'm set because I can figure out the third angle. But depending on how your mind works, you might not like figuring one of the other two angles out. You might want to focus on what's going on at the top. And to do that, we could also maybe just extend a horizontal line this way, and maybe think of extending a vertical line this way. Same rule is going to apply. The angle between the sun's ray and that horizontal line has to be 65. And so the angle left over right here would have to be 25 because they have to add up to 90. And then if you go back to geometry, these two angles are vertical angles. They have two lines that are crossing here, so the angles opposite each other have to be equal, so we get 25 degrees in here. Either way, however you're going to start looking at this, you have to come up with two of the angles inside the triangle, and then you can come up with a third one. Once we have that, it's pretty easy. I'm trying to solve for the blue H there, so I can pretty easily set up a law of sines situation here. And I might start out by saying, as an example, I know this side length, so I need to use the angle opposite it. So I'm going to set up sine of 25 degrees over 20 equals sine of 50 over h, cross multiply and divide, and I get h equals 36.25 feet. And we are done with this lesson.